Greetings and a warm welcome to all the dignitaries present here. I'm Rimpa from Clarnet, serving as the allocated session assistant to ensure a seamless experience. Clarnet proudly stands as India's most relied upon digital platform, offering a multitude of enriching services exclusively for the doctors. It is with great pride that Clarnet serves as a judge partner for this event, and the focus of today's session is physics in anesthesiology. Now, it is my pleasure to invite Dr. Meenakshi Sundaram, sir, a distinguished anesthesiologist and academic leader. Sir has served as Dean and DME at several government medical colleges, including Theni and Stanley Medical College, Chennai. He is a former national vice president of the Indian Society of Anesthesiologists and has held key positions including governing council member, president, and state secretary of ISA Tamil Nadu state branch. Now, without further any delay, sir, over to you. Thank you.
Thank you, Clinton, for the introductory remarks. And I welcome all of you for this Puthukkottai Bhudhan Second Edition, a successful webinar program which is going on. This is a second edition. Previously, we have conducted 52 webinars. And now we are in the 48th webinar. The 47th webinar of Puthukkottai Bhudhan Second Edition was held on December 10th under the topic Simulation in Anesthesia, which was also taken care of by faculty from Karnataka, but they are from Yenapoya Medical College. So the faculty being Dr. Yumna Abubakar, postgraduate, and Dr. Vinayak S. Nayak, and Dr. Tippeswamy, and it was moderated by Dr. Meghna Mugund. All the faculty were from Yenapoya Medical College, and 903 delegates attended the program live. It was a very successful program as all the people are directly exposed to the simulation lab. Same way, today, the Bangalore Medical College, which is having the highest contribution for this Puthukkottai Bhudhan Second Edition, nearly 20 faculty have participated in that, more than that. And this success story, mostly it is covered by faculty from Bangalore Medical College and the Research Institute. And today, the youngest faculty is going to be Dr. Varshini. She is the first year postgraduate. Usually, third year postgraduate will deliver the lecture. So she is a first year postgraduate because that Bangalore Medical College is having such a powerful postgraduates. So even in the first year, she is coming for that. And she has done her MBBS from Karwar Institute. And her extracurricular activities are, she is interested in reading novels like any other youngster. She is interested in reading not anesthesia texts, but she is interested in reading novels, and she is a volleyball player. I don't know, she seems to be a very short girl, but she's playing volleyball. I don't know. And the best part, which I want to really introduce, because this Puthukkottai Bhudhan, minimum it will be watched by 900 people. So Dr. Varshini is an eligible bachelor. She is yet to be married. So I want to declare that in the open forum. So I wish you all the very best, Dr. Varshini. And it will be followed by Dr. Smitha. Dr. Smitha is an assistant professor in Bangalore Medical College. And see, she has won the B.B. Mishra Award, third prize in ISACON 2021. B.B. Mishra Award is for young anesthesiologist, and even now she seems to be young, and she has won the third prize in that, and she has won the second prize in infographic competition arranged by Shivamoga branch of ISA. So one third prize, one second prize, and madam is waiting for first prize now. So I don't know when she is going to click that, and she is a executive committee member of ISA Metro. So this is the woman power. Actually, it is easy to excel in curricular activities, and by postings you can be assistant professor or professor. But she is taking active part in the association activities also. So as a president-elect, I am also happy to see her interested in this, and she's not only now, even at the junior doctor level, she was the joint secretary for Junior Doctors Association. That means, like a political party, I think she will fight for her right. And now we are happy to see her in a smile with a smiling face. But as a confrontationist, when she meets the administrator, I think she will show a different face, like a joint secretary, Junior Doctors Association. And it will be followed by Dr. Rashmi D Souza. And actually, you people should have addressed only on 24th of December. But only for this lady doctor, it was changed to 17th because madam wanted to celebrate Christmas and Dr. Smitha wanted it to be postponed to 31st. Then I only said when she wanted to have it Christmas, she will celebrate New Year Eve also. So we will push her first 17th. Then we requested the people posted for 17th to go to 24th. And we have requested them not to celebrate Christmas on 24th, 6 to 7:30. And the funniest part is the Young Anesthesiologist Award, Dr. Smitha has won the third prize in 2021. And the second prize was won by Dr.Rashmi D Souza. So it is a real coincidence. Both of them are in Bangalore Medical College. So the Bangalore Medical College takes the entire creamy layer and pushed people like me to the Tamil Nadu government, I think. So Madam is also a assistant professor in Bangalore Medical College, and she is a gold medalist in MD. Gujarat University exam. She is a gold medalist. Again, that confirms Bangalore Medical College will receive only juicy layer, creamy layer, and push the remnants to the other medical colleges. And she has won the second place, as I mentioned, in ISACON 2021 BB Mishra Award. And she is an Indian degree holder in MD. At the same time, she is a diplomat of European Society of Anesthesiology. So EDAC, everyone is now doing. She's also in that. And she has won the second prize in paper presentation in Gujarat, again in the ISACON Gujarat. So she's also waiting for the first prize. So both of them have won the second prize. And she has won the KSCH Millennium Award. And she has 3 national publications. And she is interested in obstetric anesthesia, pediatric anesthesia, and regional anesthesia. So when she has achieved this much of a distinction, what will happen to the extracurricular activities? Necessarily, the extracurricular activities will be nil, you may be thinking, but she has sacrificed all her extracurricular activities for curriculum. She has won every event in curriculum. But as a 8th standard student, in the Infosys, that is maths and logic exam conducted by Infosys, she has qualified in the first 20 in number, and again she appeared for interview and she has reached the first 10. And as a 8th standard student, she had a handshake with the Britain Prime Minister Tony Blair. So that is a great achievement. So that shows even the Bangalore Medical College is interested in taking school students. See, with the entire interest in computer, she has taken up medicine to fulfill their parents' ego. They wanted her to be a doctor anyway. The Infosys has lost a good engineer, and Bangalore Medical College got a good anesthetist. So we wish her all the very best, and she is interested in Coco also. She's a competition winner in school days. So now she will be pushing her postgraduates to go in front. So when these two APs are participating, powerful people, all medalists and prize winners, we wanted a Pakka faculty to moderate these girls, all 3. It is very difficult to manage the woman power. And another smiling face, Dr. Vinay had the courage to meet them, even though they are prize winners, for the simple reason he's a FRCA graduate. So if you are really intelligent, the entire world will respect you. And he is a fellow of Royal College of Anesthesiologists. Only very few, handful, I can say handful in India, because only 5 people may be there. As long as my knowledge goes, I can recollect 3 immediately, but I think it could be 5, like 5 fingers. So he's one among that. And he's again, he has not stopped with the curricular activity. He is a Karnataka ISA executive member, and he has authored 3 chapters for anesthesia management of neurosurgical patients. And he is a keynote speaker in all the conferences. So for all difficult locks, he is the master key. So he is a keynote speaker, but the how to sedate a crying child. So he addressed as a keynote speaker, and even is a keynote speaker for a workshop on HFNO. and focus in obstetrics. He was a keynote speaker every year. And another point, he has organized a CME on anesthesia, endocrine anesthesia. That is a difficult chapter. Endocrine anesthesia. He has done that. And necessarily, these people are having 4 national publications. These Dr. Rashmi and Smitha. He is having 14. So when these people reach the Vinay status, that is professor, as age advances, they will also reach 14. And with all these curricular activities, Dr. Vinay is interested in traveling, and she is interested in listening to music, which all of us will do. But when I travel extensively, my wife used to scold me, you are roaming all around. But now I put it in the other way. I'm interested in traveling. Like Vinay, I will place it like that. My extracurricular activity is traveling. So, with this introduction, now I hand over the session to Dr. Vinay to carry on this physics in anesthesiology. Thank you.
Good evening, everybody. Thank you very much, sir, Dr. Meenakshi Sundaram, sir, for wonderful words of appreciation and introduction for myself and all my faculty and my postgraduate. So today's topic is physics in anesthesia. So we have 3 important topics lined up. One is humidifiers, which we all use on a practical day-to-day use, which will be covered by Dr. Varshini, our first-year postgraduate resident. Then gas laws and their applications by Dr. Smitha. And lastly, we have the fluid mechanics, pressure and fluid mechanics will be covered by Dr. Rashmi. So over to Dr. Varshini for humidifiers.
Good evening, everybody. Today I'll be talking about the topic on humidifiers. Humidity is a general term. It is used to describe the amount of water vapor present in a gas. It is described in 2 terms. One is absolute humidity and relative humidity. Absolute humidity is defined as actual mass of water vapor present in a known volume of gas. And the absolute humidity in the upper airway in humans, it amounts to about 34 grams per meter cube, and it reaches to a peak of 43 grams per meter cube when it reaches to the alveoli. And the second term is relative humidity, which is defined as a ratio of the mass of water vapor in a given volume of gas to the maximum amount of water vapor that it can hold at the same temperature. And it is expressed as a percentage. The basic few definitions which we have to know is a gas is a state of matter which is formed when a liquid is heated above its critical temperature, and vapor is the matter in its gaseous state below its critical temperature. The critical temperature is the temperature above which the vapor can no longer be liquefied with any amount of pressure applied on it. Vapor pressure, it is the pressure exerted by the molecules that have left the liquid phase in favor of the gaseous phase, and it is expressed in kilopascals. The saturated vapor pressure is the vapor pressure when the liquid and vapor phase are in equilibrium. Latent heat of vaporization is the heat required to convert 1 gram of substance from the liquid to the gaseous form, and it is expressed as joules per gram. Boiling point is the temperature at which the saturated vapor pressure equals to the ambient pressure. The importance of humidification is that heat and moisture extent. It is the primary function of the upper airway tract, mainly the nose. The nose, it heats and humidifies the inspired air, and it cools and reclaims the water when the gas is expired. The air we breathe, it is fully saturated with water vapor as it passes through the nose to the alveoli. And it mainly maintains the humidification mainly maintains the mucosal integrity, ciliary activity, and prevents the drying of the secretions and helps in easy expulsion of the secretions. The nasal mucosa lining, it is kept moist by the secretions by the mucous glands, goblet cells, and transduction through the cell walls, and condensation of exhaled humidity. The nasal mucosa, it is very vascular, and actively it regulates the temperature changes in the nose, and it promotes the effective heat transfer. Mainly the mucosal lining of the sinuses and the bronchi, it aids in heating and humidifying inspired air. As we inspire gas, it moves into the lungs and it reaches, achieves the body temperature, that is 37 degrees Celsius, barometric pressure, and it gets saturated with water vapor. So it achieves the BTPS conditions, that is 100% relative humidity at 37 degrees Celsius. This point, it is approximately 5 centimeter below the carina, and it is called as isothermic saturation boundary, that is ISB. Above this, the temperature and humidity decreases during inspiration and increases during expiration. Below this, it is constant. During inspiration through the nose, the tortuous path through the terminates. It increases the contact of the inspired air to the mucosa, and it warms and humidifies the air, and it cools the mucous surface. During exhalation, the expired air, it transfers the heat back to the cooler trachea and nasal mucosa by convection. And as the saturated gas cools on the mucosal surface during exhalation, and the water vapor gets reabsorbed by the mucus. So a total of 250 ml of water is lost, and 360 kilocalories of energy is used in this process of humidification. When we use endotracheal tubes and supraglottic airways, this is bypassed, and this role is taken up by the tracheobronchial mucosa. So adequate humidification, it is an important consideration in delivering the anesthesia gas during the supplemental oxygen therapy to the patients requiring additional respiratory support, including mechanical ventilation. The complications of breathing dry air is it damages the respiratory tract. There will be loss of body heat, absorbent desiccation, and tracheal tube obstruction. So when we inspire dry air, it causes the secretions to thicken, and it impairs the ciliary function, which results in impairment of surfactant activity and susceptible injury to the ciliary function, which leads to poor mucus clearance. It results in airway obstruction and atelectasis, and the mucus plugs becomes a potential sites of infection. Dry gas can also cause bronchoconstriction and compromise the respiratory function. The effect of excess humidification is that it causes ciliary degeneration and paralysis. It can lead to pulmonary edema, altered alveolar arterial oxygen gradient, and decreases the vital capacity and compliance. It also decreases hematocrit and serum sodium. There are different sources of humidity. The carbon dioxide absorbent, it reacts with carbon dioxide and liberates water. And water is contained in the absorbent granules since the reunification of the inspired. And the exhaled gases during the rebreathing in the tracheal tube or in the supraglottic airways, almost half of the humidity of the expired air is preserved in this manner. In the systems that allow rebreathing of the exhaled air, the humidity and temperature of the gases, they are preserved, and relative proportions of the fresh gas, and it depends on the relative proportions of the fresh and expired gases. As the fresh gas flow is increased, the inspired temperature and humidity will be reduced. We can rinse the inside of the breathing tubes and the reservoir bag with water, and this can increase the humidification of the inspired air. Using low fresh gas flows with the circle system can also preserve the moisture. With low flows helps in humidification of the inspired air. The Bain circuit, which is the coaxial modification of the Mapleson D circuit, it is not optimal because it needs higher fresh gas flows. Types of humidifiers, it can be divided into active or passive, or heated or unheated. In active type of humidifier, the heat is actively added or water is actively added. The examples are bubble humidifiers, passover humidifiers, nebulizers, and vaporizers. In passive humidifiers, there will be recycling of the exhaled heat and humidity from the patient side. Examples are HME filters. These are the components. There are different components of the humidifiers. One is humidification chamber, which contains the liquid water. It may be some humidifiers may have an integral part which supplies the liquid water to the humidification chamber. The heat source will be supplied either by the rods immersed in the water or a plate at the bottom of the humidifier. The inspiratory tube, it will carry the humidifier gas to the patient, and if it is not heated, the gas will cool and lose some of its moisture as it reaches to the patient end. And this water may collect in the inspiratory tubing, so a water trap will be necessary when using such humidifiers. A heated wire inside the inspiratory tube is most often used, which will be close to the patient end. If the gas temperature delivered to the patient is set above this temperature of the humidification chamber, 100% relative humidity will be delivered. There are also temperature monitors, which helps in measuring the gas temperature at the patient end of the breathing circuit. And these sensors are in the water reservoirs or in the contact with the heater plates. There are also thermostats, which are divided into servo-controlled units or non-servo controlled units, which automatically regulate the heating element of the humidifiers. Servo-controlled, they automatically regulate the heating element of the humidifier in response to the temperature changes near the patient end of the probe. These also have alarms, which help in monitoring the temperature. In non-servo controlled units, the power is required and it is according to the setting of the control, irrespective of the delivery of the temperature at the patient end. There are different kind of controls and alarms. Most humidifiers, they allow the temperature selection at the end of the delivery tube or at the humidification chamber. Some allow less than 100% relative humidity to be delivered. And these alarms, they warn when the temperature at the patient end of the circuit, which deviates from the set temperature, or when the temperature probe is not at the place, or when the water level in the humidification chamber is at the lower end, or when the airway temperature probe does not sense any increase in the temperature with any certain time. A low temperature alarm will help to detect problems with the heater element. There are different standards for the humidifier. The humidifier must be capable of producing an output of at least 10 mg H2O per liter. And those intended to use with supraglottic airway, they should at least produce an output of 33 mg water per liter. The average temperature at the delivery tube should not fluctuate more than 2 degrees Celsius from the set point. The volume of the liquid exiting the humidifier shall not exceed 1 ml per minute or 20 ml per hour for humidifiers for use in the units, or 5 ml per minute or 20 ml per hour for all other humidifiers. If the humidifier is heated, the temperature at the delivery tube, it should not exceed more than 41 degrees Celsius. And this will be taken up by the temperature alarms. The accessible surface temperature of the delivery tube, it should not exceed 44 degrees Celsius within 25 centimeter of the patient connection port. When the humidifier is tilted 20 degrees from its normal operating position, there should be no water spillage from the breathing circuit. And all calibrated controls, they can vary up to plus or minus 5 degrees, except for the temperature, which should be accurate as to plus or minus 2 degrees Celsius. The direction of the flow must be marked on the humidifiers with the flow direction sensitive components. In any circle system, a humidifier is placed in the inspiratory limb downstream of the unidirectional valve using an accessory breathing tube. In Mapleson system, it should be placed in the fresh gas supply tube. The bubble-through humidifier is a type of unheated humidifier, active type of humidifier, which is used in oxygen delivery system. Unheated, it can produce absolute humidity levels between approximately 15 mg per liter and 20 mg per liter. At the room temperature, 10 mg per liter absolute humidity, it corresponds to approximately 80% of the relative humidity. In passover humidifier, there is a gas which flows over the surface of the volume of water. And this gas fluid interface is usually limited. These are typically heated for the use with mechanical ventilation, but they may also be used with room temperature fluids with non-invasive ventilatory support. The advantages of this is most of the heated humidifiers, they are capable of delivering a saturated gas at body temperature or above, even at high flow rates. A heated humidifier, it can also be more effective in humidification than in HME filters. And some can also be used in spontaneously breathing and tracheostomized patients. The disadvantage is that it is very bulky and it's complex, and it has high maintenance cost, and there is increased work. Example for temperature uh, and reservoir exchange, draining the condensate, and changing the water traps. Little protection against the heat loss during the process. The hazards are infection, breathing system problems, water aspiration, overhydration, thermal injuries, overheated inspired air, increased work of breathing, the monitoring interference, high humidity, and it can also alter the anesthetic agents such as halothane as it passes through the humidifier and comes in direct contact with the gas at the temperature of 68 degrees Celsius or higher, and equipment damage or malfunction. The heat and moisture exchangers are passive type of humidifiers. They capture the heat and moisture which is coming from the expired gas from the patient and returning up to 70% of the humidification. There are three types of HMEs: simple condenser humidifiers, hygroscopic condenser humidifiers, and hydrophobic condenser humidifiers. The simple humidifiers, they contain condenser element with high thermal conductivity, which is usually made up of metallic gauze, corrugated metal, or parallel metal tube. And on exhalation, the expired water vapor, it condensates on the surface and rewarms it. On the next inspiration, the cool and dry gas, it is warmed and humidified as it passes over through the condenser element. And it is only 50% effective. The hygroscopic condensers, they are made up of low thermal conductivity elements like paper, wool, or foam, and they are impregnated with the hygroscopic salts like calcium and lithium chloride. So by these hygroscopic salts, they retain heat and moisture from the exhaled gases. So during exhalation, some water vapor condenses over the cool condenser element, and some directly bind to the hygroscopic salt. And during the next inspiration, the lower water vapor pressure in the inspired air liberates water molecules directly from the hygroscopic salt without any cooling. They are 70% efficient. They have 70% efficiency. In hydrophobic condenser humidifiers, they use a water repellent element, and they are of low thermal conductivity. During exhalation, the condenser temperature increases to
interrupt, Dr.
approximately...
Varshini. Can you please speed up a bit more?
Yes, sir. It increases to the approximately 25 degrees Celsius because of the condensation and a latent heat of condensation. On inspiration, the cool gas and evaporation cools the condenser down to 10 degrees Celsius. So this large temperature change, it results in conversion of more water and humidifies the next breath. And it is also 70% efficient. The indications is it can increase the... It can be used in short and long-term ventilation, and it is helpful for transporting intubated patients. The contraindications may be usage of this in thick, copious bloody secretions, and during the patients, we should be cautious when we are using it with the patients who have increased secretions. It is less expensive and easy to use, lighter weight. They also have less resistance when dry. They do not require water or any source of energy. There is no danger of overhydration or hyperthermia. They also access barriers like bacterial and viral filters. They also reduce problems caused by the humidity in the breathing system, such as obstruction or of ventilator malfunctions. The disadvantages, they are not as efficient as active humidifiers. Nebulizers or other example, it emits water vapor in the form of aerosol mist. The commonly used or pneumatically driven or ultrasonic nebulizer. Both can be heated. A pneumatic nebulizer, it works by pushing a jet of high pressure gas into the liquid, inducing shearing forces and breaking the water up to its fine particles. Because of high flow, it must be used with the pneumatic nebulizer. It must be placed in fresh gas flow line. And in ultrasonic nebulizers, it produces fine mist by subjecting the liquid to high frequency, electronically driven
Varshini,
ultrasonic.
can you please summarize your talk quickly? Move on to the next speaker, please.
Yes, sir. Uh, uh, Sir, the humidifiers, they are usually used for humidifying the inspired air, especially when the patient is intubated or when we are using the supraglottic airways, because the gases which we medical gases which we use for anesthetizing the patient, they are usually dry and they are not humidified clearly. So humidification is very important to make sure that the gas which we are delivering is not making the patient's airway dry, and it is not causing the patient's secretions to uh, 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 it is not making the
Okay.
patient's airway to dry, sir. So
Okay. Okay. Thanks, Dr. Varshini, for your wonderful talk on humidifiers. So Dr.
thank you.
Varshini has basically covered what is humidity, difference between absolute and relative humidity, the ISP point. She's covered the difference between active and passive humidifiers, emphasized the role of HME filter, which is probably the most common type of humidifier which we all use on a day-to-day anesthesia practice. The only thing to add to our talk is ideal properties of a humidification device. Just like ideal properties of a gas, ideal properties of a vaporizer, we also have ideal properties of a humidification device. They are, first of all, it should have the ability to warm and humidify gases to physiological conditions. That is, body temperature, that is 37 degrees Celsius. It should not offer any additional resistance to gas flow. There should be no additional dead space. There should be no additional risk of infection. And it should be easy to use. It should not be sophisticated or complicated. Anybody and everybody should be easy to use. So easy and safe to use, and it should be cost effective. I think in this regard, obviously, none of the devices will satisfy all the properties, but I think HME filter covers most of it. So that's why we use it very commonly. But of course, it's a passive humidifying device with its limitations. So I think so that covers the humidifiers. Next, we will move on to the very important topic, that is gas loss and anesthesia application by Dr. Smitha. Over to you, Dr. Smitha.
Yes, sir. A warm good evening to everyone. So let's look into gas loss and anesthesia. So before going into gas loss, let's see what is a matter. Matter is anything that has a mass and occupies a space, consisting of microscopic atoms and combination of atoms. So what is an atom? They are the building blocks of any substance, which consists of a nucleus consisting of positively charged protons and neutrally charged neutrons, and the negatively charged electrons orbit around this nucleus. And what is a molecule? Molecule is a group of two or more atoms chemically bonded together, forming the smallest unit of a substance that retains its chemical structures even after division. So how are the molecules arranged across the states of matter? In solid, the particles, the atoms or the molecules are tightly packed in the form of a lattice. They have a definite shape and volume, and each molecule vibrates or oscillates in a fixed or a mean position. But when heat is added to solid, each molecule vibrates with a greater amplitude and takes up a greater space, so that molecules move further apart, melting down the lattices into liquid. And in liquid, the molecules still exert some force on each other, and these forces of attraction between them is called as van der Waals forces. When heat is applied to the liquid, these molecules gain further kinetic energy and eventually overcome the van der Waals forces exerted by the neighbors. And they will be able to move about in the space in the gas form. So in gas, atoms and molecules are far apart, moving rapidly and freely. They don't have a definite shape, and they take the shape of the container. At the interface between the liquid and the gas or the vapor, there will be a molecular exchange, so that the molecules at the surface of the liquid occasionally escape into the gas by gaining kinetic energy. Conversely, molecules in the gaseous phase may transfer into liquid by losing out some kinetic energy. There occurs a temperature at which equilibrium occurs between these two rates of molecular transfer. At this temperature, the vapor above the liquid is said to be saturated. And the pressure of the gas at this temperature is known as saturated vapor pressure. And when liquid is heated to its boiling point, almost all the molecules gain more kinetic energy, so that all of them transfer into gaseous phase. So coming to the kinetic molecular theory of gases. The molecules in a gas act like minuscule rubber balls undergoing elastic collisions with each other, and that without of the container walls at frequent intervals. The result of these collisions between the gas molecules and the walls of the container is that a force is exerted on the wall. And that force exerted on a certain area is defined as the pressure. And the molecules have certain kinetic energy of the motion which determine the temperature of that gas. And the amount of the space occupied by the gas determines its volume. So we will be discussing about the pressure, temperature and the volume of the gas in this lecture. So what are the properties of an ideal gas? The molecules are assumed to be so far apart in a gas that there is no attraction between them. And the volume of the molecules themselves is so negligible compared to the volume of the gas. And the molecules are always in the random motion, obeying Newton's laws of motion. But ideal gases do not really exist in nature. However, the real gases behave almost similar to ideal gases in most of the conditions, except at very low temperatures, at very high pressures, and when gas is on verge of becoming liquid, that is at condensation. So we come to a point of standard temperature and pressure. So what is standard temperature? It is 273 Kelvin or 0 degrees or 32 Fahrenheit. So Kelvin, the relationship between the Kelvin and Celsius is Kelvin is equal to Celsius plus 273. And the standard pressure at sea level is 760 millimeter of Hg or 1 atmosphere or 101.3 kilopascal or 14.7 psi. So let's consider a scenario wherein there is a container containing a gas with a volume V1 and the pressure is P1, and the pressure is the result of the collision of molecules between them and that width of the container at temperature T. Now when we decrease the volume of this container, the collisions between these molecules increase, thereby increasing the pressure. However, to note is that the temperature is constant. This is Boyle's law. So it states that at constant temperature, the pressure is inversely proportional to the volume of the gas. That is, P is inversely proportional to V, PV is equal to constant. So that P1 into V1 is equal to P2 into V2. And the hint to remember Boyle's law is water boils at constant temperature at sea level. So in Boyle's law, the temperature is constant and the other two variables are inversely proportional. So when and all we can apply Boyle's law. Boyle's law is applied to calculate the amount of gas in the cylinder in the work of breathing and also in scuba diving. Let us look into each of them. So to calculate the amount of gas present in the cylinder, let us consider a cylinder with a question. So here a partly used E oxygen cylinder has a pressure of 1500 psi with an internal volume of 5 liters. The second part is if the oxygen was required at a flow rate of 2.5 liters per minute roughly, how long would the cylinder last? So what do we have here is the pressure gauge reading is the cylinder pressure is 1500 psi and the internal volume is 5 liters. So we need to find the volume of gas in the cylinder that would expand to if it were at the atmospheric pressure. And what is the atmospheric pressure? So since this is in psi, so atmospheric pressure in psi will be 14.7 psi. So according to Boyle's law, the product of pressure and volume in the cylinder must be equal to the product of pressure and volume outside the cylinder. So cylinder pressure becomes P1, cylinder volume becomes V1, atmospheric pressure becomes P2, and the volume we need to find out is the V2. So with this formula P1 V1 is equal to P2 V2, we get a V2 reading of 510 liters. That is 510 liters of oxygen will be available. So now then for the next part of the question, so if the flow rate is 2.5 liters per minute, so the flow rate which is given by volume by time, so how long the cylinder would last? So that is how long this 510 liters of oxygen would last. So by rearranging, time is equal to volume by flow rate. So we get a time of around 204 minutes. Coming to the second example, during work of breathing, so the atmospheric pressure is 760 millimeter of Hg. And if even in the lungs, if it is 760 millimeter of Hg, then there won't be any inspiration or expiration. But during inspiration, the diaphragm contracts, so thereby increasing the intrathoracic volume. So since intrathoracic volume increases, the intrathoracic pressure decreases to 757 and the inspiration occurs. Whereas during expiration, as the diaphragm relaxes upwards, there is decrease in the intrathoracic volume, as a result of which there is increase in the intrathoracic pressure, leading to expiration. The next and the third example is the scuba diving. As we can see in this picture, so where at the surface, the pressure is at 1 atmosphere and the volume of the bubble is 100%. As the depth increases, the pressure starts to increase, whereas the volume of the bubble starts to decrease. So for every 10 meter increase in the depth, the pressure increases by 1 atmosphere. So when the diver descends down due to increase in the pressure, the air bubbles which decrease in their size, so get dissolved in the blood and the tissues. And as he ascends up, so all these bubbles at the lower pressure, they expand their volume, leading to decompression illness. So coming to the next scenario, wherein a container consists of a gas with the volume V1 and the pressure P and the temperature is T1. Here when we apply a heat, that is T2, which is T2 is more than T1, the molecules gain extra kinetic energy so that the pressure should increase. In order to keep the pressure constant, so the volume should increase. This is Charles' law, that is at constant pressure P, the volume of the gas is directly proportional to the temperature T. That is, V is directly proportional to T, V by T is a constant, so that V1 by T1 is equal to V2 by T2. And the hint to remember Charles' law is, King Charles is under constant pressure to be a king. So in Charles' law, the pressure is constant and the other two variables are directly proportional. And where do we apply Charles' law? In case of hot air balloon, heat loss in anesthetized patient and Bourdon thermometer. So what happens in a hot air balloon? When it is heated, there is increase in the temperature and the gas inside the balloon is heated and it expands, increasing the volume. And expanding air causes some air inside the balloon to escape at the base to maintain the pressure. So, and as it expands, hot air inside the balloon becomes less dense than the outer cold air. So it rises and taking the balloon up. The second example, the convective heat loss in anesthetized patient. The air around the patient is warmed by radiation and conduction from the patient's skin. This causes the air around the patient to expand, reducing its density and causing the warmed air to raise away from the patient through convection. The third example being in the Bourdon thermometer. So this is the thermometer, this is the sensor and this is the indicator. The inside of the sensor has a volatile fluid. So when the temperature increases, this volatile fluid is converted into vapor. The vapor pressure increases, the volume of the vapor increases so that it passes through a flexible Bourdon tube which is connected to the indicator through a movable end indicating the temperature. The next scenario is there is another container with the gas. So with the pressure of P1, temperature is T1 and the volume is V1. If heat is added to this and the volume is kept constant, so the molecules gain the extra kinetic energy and their rate of collisions between them and that width of the wall increases, thereby increasing the pressure. This is Gay-Lussac's law or the pressure law, which states that at constant volume of gas, the pressure is directly proportional to the temperature. P is directly proportional to the temperature. P by T is a constant. So that P1 by T1 is equal to P2 by T2. It is applied in filling of the cylinders. So consider a cylinder. So a cylinder has a constant volume V. So if at all there is any increase in the temperature, the pressure inside the cylinder increases. And if it increases to the critical level, the cylinder will rupture at its weakest point, leading to explosion. Hence, cylinders should be filled at the ambient temperature at which they are stored and used, and also filled according to the respective filling ratios. The next scenario is we have two containers containing two different gases, gas A and gas B. Gas A has a pressure of P1, that is 1 bar, and gas B has a pressure of P2, that is 2 bar, and the volume and temperature are kept constant. So if we mix these two gases in a container with the same volume and the same temperature, then the total pressure will be equal to the sum of the partial pressure of the constituent gases. This is Dalton's law of partial pressures. It states that in a mixture of gases, the pressure exerted by each gas is the same as that it would exert if it alone occupied the container. So this pressure P1 was 1, P2 was 2. So therefore, when it was mixed, so the pressure total was 3. And in the mixture, each molecule contributes to the total pressure exerted on the wall. Each molecule behaves independently of its neighbors, and each molecule exerts the same pressure whether the other type of molecule is present or not. So in other words, the total pressure will be equal to the partial pressure of its constituent gases. So it's applied in the partial pressures of air. The air has an ambient atmospheric pressure of 101.3 kilopascals. So it is due to the sum of the result. It is due to the sum of the partial pressures of the constituent gases. Oxygen at 20.9 kilopascals, nitrogen at 78.1 kilopascals, argon at 0.97 kilopascals, water at 1.28 kilopascals, and carbon dioxide at 0.05 kilopascals. This Dalton's law can also be applied in the humidification of air in the lungs. So with the ambient temperature of 22 degrees, the relative humidity in the atmosphere will be 50%. So the inspired air has a partial pressure of water of 1.3 kilopascals, and that of oxygen will be 20.9 kilopascals. As the air enters the pharyngeal area, so where the temperature rises to 30 degree, the relative humidity increases to 95%, and by the time it reaches the carina, where the temperature is 37 degrees Celsius, the relative humidity will be 100%, so that there will be complete humidification of the inspired air, leading to increase in the partial pressure of water by 5 kilopascals, so that the partial pressure of water is increased to 6.3 kilopascals in the lungs when compared in the inspired air. This extra water vapor displaces the other gases, so that the overall pressure remains the same, that is at 101.3 kilopascals. So this humidification of air in the lungs alters the percentage of oxygen. As we know, the inspired air consists of a partial pressure of oxygen of 20.9 kilopascals, so that the percentage of oxygen in inspired air will be 20.63% of oxygen. However, after humidification of air in the lungs, the partial pressure of the percentage of the oxygen drops to 19.7% of oxygen. So nearly there is 1% drop in oxygen percentage. This reduction in the oxygen partial pressure can have severe consequences, especially at the higher altitudes, where the partial pressure of oxygen itself is very low in the inspired air. Coming to the next scenario, so we have three balloons containing three different gases, helium, oxygen, and xenon. All have different atomic mass and numbers, and they all have different molecular weights and the masses. So but the thing is, they all have the constant volume V and the constant value of the pressure and the temperature. And it is stated that at this constant volume and pressure and temperature, all the gases have equal number of molecules. This is given by Avogadro's hypothesis, which states that equal volumes of different gases at the same temperature and pressure contain equal numbers of molecules. And this measure is called as mole. So what is a mole? Mole is the quantity of the substance containing the same number of particles as there are in a 12 grams of carbon 12. So which is equal to 6.022 into 10 to the power of 23. This is the Avogadro's number. So 1 mole, as we know, it has 6.022 into 10 to the power 23 molecules. So which will equate to 1 molar mass, which will equate to molecular weight of that substance in grams. So that 2 grams of hydrogen, so wherein the molecular weight of hydrogen is 2, 32 grams of oxygen with a molecular weight of 32, 44 grams of nitrous oxide with a molecular weight of 44, 18 grams of water with a molecular weight of 18, 184 grams of isoflurane with a molecular weight of 184, all constitutes 1 mole. And also it is stated that 1 mole occupies 22.4 liters at standard temperature and pressure. And the relationship between the mass of the substance and the molar mass is mass of the substance is equal to the molar mass into number of molecules. So this is another illustration of Avogadro's law. So wherein the volume of an ideal gas is directly proportional to the number of the moles possessed, assuming constant temperature and pressure. That is, V is proportional to N. Avogadro's hypothesis can be used in calibration of the vaporizers. So here is a vaporizer with a halothane of 19.7 grams, and the oxygen is flown through the vaporizer at the rate of 224 liters. So now the question is, what will be the mean percentage of concentration of halothane? So first we need to find out what is the mole or the molar mass of this halothane. The molecular weight of halothane is 197. So that the molar mass, that is molecular weight in grams, will be 197 grams. This is 1 mole. So this 1 mole occupies 22.4 liters at standard temperature and pressure. Now this 19.7 grams will be 0.1 mole because the mass of the substance is equal to molar mass into number of moles. So hence the number of moles will be mass of the substance by the molar mass. So hence this 19.7 grams of halothane in the vaporizer is 0.1 mole. So hence, 1 mole occupies 22.4 liters at STP. So 0.1 mole occupies 2.24 liters. And this 2.24 liters of halothane is vaporized in 224 liters of oxygen. So therefore, the percentage or the concentration of the halothane will be 1%. So another usage of Avogadro's hypothesis is to calculate the volume of nitrous oxide gas in the cylinder. So a full nitrous oxide cylinder weighing 3.4 kgs. So if we have to find the volume of the nitrous oxide gas, that is because the nitrous oxide stays in the form of both liquid and vapor. So coming to the calculation, molecular weight of the nitrous oxide is 44. So hence 1 mole of nitrous oxide will be 44 grams, that is molecular weight in grams, which occupies 22.4 liters of volume at standard temperature and pressure. So 3.4 kgs or 3400 grams of nitrous oxide occupies 1730 liters of nitrous oxide at standard temperature and pressure. However, at 15 degrees, this is about 1800 liters. So it can be calculated by substituting the temperature to 15 degrees Celsius. So in practice, the weight of the nitrous oxide is used to indicate how full the cylinders are. So the weight of the empty cylinder is known as the tar weight. So the another next scenario is, so if we have to fill the nitrous oxide and the oxygen cylinders under pressure at 20 degrees Celsius. So during filling of the nitrous oxide under pressure at 20 degrees Celsius, after reaching certain pressure, nitrous oxide liquefies even without further increase in the pressure until the cylinder is filled to the appropriate level. But however, while filling oxygen under pressure at the same temperature of 20 degrees Celsius, that is at the room temperature, so oxygen will be in the gaseous form only, and the pressure gauge reading indicates accurately how full the cylinder is. And no matter how much ever pressure we applied, it is impossible to turn oxygen into liquid at this room temperature. But however, if we fill oxygen under pressure at very low temperatures like minus 19 degrees Celsius, then oxygen liquefies. So here comes the concept of critical temperature. What is critical temperature? It is the temperature above which a substance cannot be liquefied, how much ever pressure is applied. However, at or below this temperature, substance liquefies even if there is no further increase in the pressure. In other words, above the critical temperature, the substance will be in gaseous form, and below the critical temperature, the substance will be in the vapor or the liquid form. And each gas has its own critical temperature. And the pressure of the substance at this critical temperature is known as critical pressure. So hence, coming back to this example, the critical temperature of the nitrous oxide is 36.5 degrees Celsius. So that is at room temperature, which is 20 degrees Celsius, which is less than its critical temperature. The nitrous oxide will be in its liquid form. But as in tropical regions where the temperature is above 36.5 degrees Celsius, nitrous oxide will be in the gaseous form even inside the cylinder. And the critical temperature of the oxygen is minus 119 degrees Celsius. So here is the graph showing the large syringe of nitrous oxide, graphically showing the results of compression of this syringe on the pressure. And this is the line showing the changes of the pressure with the changes in the volume at the temperature which is above 36.5 degrees Celsius. So since it is above its critical temperature, nitrous oxide will be in the gaseous form, and since it is in the gaseous form, it obeys all the gas laws and it obeys the Boyle's law. And if such lines, series of lines of pressure versus volume are produced at various temperatures, it is known as isotherms. So let us look into the isotherm of a nitrous oxide. So with the critical temperature of 36.5 degrees Celsius, at 40 degrees Celsius, which is above its critical temperature, it's in the gaseous form. So it follows the Boyle's law, that is, if any decrease in the volume increases the pressure, and the curve produces a rectangular hyperbola. Whereas at the critical temperature of 36.5 degrees Celsius and the critical pressure of 73 bar, the nitrous oxide liquefies. However, this liquid is relatively incompressible compared to the gas, so any slightest decrease in the volume increases the pressure significantly. So almost a vertical line occurs. However, at the room temperature of 20 degrees Celsius, as nitrous oxide is steadily compressed to the pressure of 52 bars, some of it liquefies, containing both the liquid and vapor. And any further decrease in the volume causes more vapor to condense into liquid without altering the pressure. So almost a horizontal line is present at 52 bar. And this is the pressure in the typical nitrous oxide cylinder at room temperature, being its saturated vapor pressure. And when all the nitrous oxide vapor is condensed to liquid, then any attempt to reduce the volume will result in the sharp increase in the pressure, so which is indicated by a sharp vertical line. So the critical temperature, so anything above will be in the gaseous form, anything below will be in the vapor or the liquid form. And if the room temperature is more than the critical temperature, then the substance will be in the gaseous form. So the examples are oxygen and nitrogen. Whereas if room temperature is less than critical temperature, so they will be in the vapor form. Example will be nitrous oxide and carbon dioxide. Let's consider a hypothetical case, so wherein the nitrous oxide is filled completely until its brim in the liquid form. So if there is any increase in the temperature, the liquid nitrous oxide expands, but unlike gas, it is not compressible. So there will be great increase in the pressure as we seen in the last graph, so leading to explosion. Hence, to mitigate this risk, manufacturers always ensure that the cylinders are partially filled with the liquid nitrous oxide in order to leave room for the nitrous oxide vapor above the liquid. So that if there is any increase in the temperature, as the liquid expands, it compresses the vapor above, and as the vapor is compressed, so it condenses back into liquid, so as the pressure is maintained. In practice, nitrous oxide cylinders are filled according to their weight, and for a given size of the cylinder, there is a fixed quantity of nitrous oxide so that there is no risk of explosion. So this is by the filling ratio. It is the weight of the fluid in the cylinder divided by the weight of the water required to fill the cylinder. In cold countries, it is filled up to 75%, then whereas in the tropical countries, it is up to 67%. So as we know, all the laws, the product of pressure into volume is a constant. Boyle's law, V by T is a constant, P by T is a constant. So if we combine all these three, so we get PV by T is a constant. This is the combined gas law. So this constant applies to the fixed amount of gas, and if the amount changes, the value of the constant also changes. But however, this law, that is PV by T is a constant, remains valid still. And we also know the Avogadro's law, that volume is directly proportional to N, that is the amount of the gas in moles, and the constant R, which is the proportionality factor or the universal gas constant R, with a value of 8.31 joules per Kelvin per mole. And if we combine these two, so we get that constant is equal to nR. And if we substitute here, so PV by T is equal to nR, and we get PV is equal to nRT, which is the ideal or the universal gas law. This combined gas law requires the amount of the gas to be constant. So note that it is not the volume but the amount of the gas, so that we can quantify the behavior of the single quantity of the gas under two different conditions. That is P1 V1 by T1 is equal to P2 V2 by T2. So where the temperature must be in Kelvin, pressure and volume can be in any other units, provided both are in the same units on either side of the equation. So let's take an example for this. There is a 4 liter of gas collected at 37 degrees Celsius and 760 millimeter of Hg. So what is the volume of gas at standard temperature and pressure? So here there are two conditions, one at this temperature and pressure and one at the standard temperature and pressure. So we have P1 is equal to 760 millimeter of Hg and T1 is 310 Kelvin. So as we know, temperature should be in Kelvin. So what is given is 37 degrees Celsius. So if we add 273 Kelvin, so we get 310 Kelvin and the volume is 4 liters. And standard temperature is 273 kelvins, standard pressure is 760 millimeter of Hg. This is also in millimeter of Hg, hence this is also millimeter of Hg. And what we have to calculate is the volume. So if we substitute the values, we get the volume of 3.5 liters. Hence, this equation, that is PV is equal to nRT, allows us to calculate the volume from a known pressure of a gas or the vice versa if the temperature and the amount of the gas are known. And the value of this R changes according to the SI unit of the pressure used. If the pressure is in atmosphere, this value of R to be used. If the pressure is in millimeter of Hg, this value of the R to be used. And if pressure is in kilopascals, so this value of the R to be used. So let's apply PV is equal to nRT for the cylinder. Here, the gas has a fixed volume, that is V, and the temperature is fixed at the constant temperature. R is a constant. So the remaining ones are P and N, so that the pressure is directly proportional to the N, the number of moles of gas or the amount of gas in the cylinder. So hence this pressure gauge acts as the gauge of the contents of the cylinder, provided that it should only contain gas, not a liquid or a vapor. So another application of PV is equal to nRT is to calculate the volume occupied by 1 mole of any substance, that is Avogadro law. We know that 1 mole occupies 22.4 liters at STP. So let us look how we can derive at it. So let's take an example of nitrogen. What volume V would 28 grams of nitrogen occupy at STP? So first we need to calculate N, that is the what amount of mole it is. So number of moles is equal to mass of the gas by the molar mass. So to calculate molar mass, let us look into what is the molecular weight of nitrogen. Nitrogen has an atomic mass of 14, but in molecule it is diatomic, that is N plus N, 14 plus 14, it will be 28. Hence, N will be mass of the gas. The mass of the gas given is 28 grams. Molar mass will be 28, so it is 1 mole. And the other units are under SI units, the standard temperature will be in Kelvin, 273 Kelvin. Standard pressure at sea level, 101.3 kilopascals, and volume should be in cubic meters, and R is a constant with this value. Since the pressure is in kilopascals, this is the value of the R to be used. And if we substitute these values in PV is equal to nRT, so we get the volume of 22.4 liters. So hence, if N is 1, then PV is equal to RT. So at standard temperature and pressure, volume V will invariably be 22.4 liters. So to summarize, the Boyle's law, the pressure is directly inversely proportional to the volume. Charles' law, volume is directly proportional to the temperature. Pressure law, pressure is directly proportional to the temperature. So if we combine, we get the combined gas law. And for the same gas under two different conditions, P1 V1 by T2 is equal to P2 V2 by T2. And if we add the Avogadro's law and the molar gas constant, we get the universal gas law, PV is equal to nRT. And where we have to use PV is equal to nRT and where we have to use combined gas law. PV is equal to nRT, so it applies to the ideal gases under various conditions. So in the problems where we know the state of the variables of a gas at a particular point of time, whereas the combined gas law, so wherein there is a two different conditions. So one we have an initial condition and then we have a final condition. So and in the problems involving process where a gas changes from one set of condition into another. These are my references. Thank you.
Thank you, Dr. Smitha, for a wonderful insight into gas laws and their applications in anesthesia. Dr. Smitha has covered in detail, right from literally from the atomic concept, the molecules, how they're arranged, properties of an ideal gas. She covered the Boyle's law and its applications, Charles' law, Gay-Lussac's law, adiabatic changes, Dalton's law of partial pressures. She covered Avogadro's hypothesis, Avogadro's number, and lastly combined gas laws into the concept of universal gas constant. Also, she spoke about critical temperature and critical pressure. Now, I just wanted to add just one more two applications of Boyle's law, which practically we use in anesthesia. One is, what is the reason we use saline in the endotracheal tube cuff when we shift an intubated patient into a hyperbaric chamber? Like, for example, in burns patients, is application of Boyle's law, we know that pressure is inversely proportional to volume. So in a hyperbaric chamber, as the pressure is high, volume of the gas inside of the air inside the endotracheal tube cuff comes down. So that is the problem when the tube starts leaking. So to prevent that, that is why we fill the endotracheal tube cuff with saline. Okay, that is one practical application. The other is when in the emphysematous bullae patient, as a patient climbs to a high altitude, something like 8,000 feet, again pressure is inversely proportional to volume. So high altitudes, pressure is low, volume goes up. So the volume of the gas in the bulla expands so much so that it can cause a rupture and can cause a pneumothorax. These are only two things I thought I will add. Otherwise, you've covered all the applications very beautifully with wonderful diagrams. And this is a very important topic for the postgraduates. Now,
Thank you, sir.
Yeah, thank you. Thank you, Dr. Smitha. Let's quickly move on to the next important topic for the day. That is the pressure and fluid mechanics, which will be covered by Dr. Rashmi. Over to you, Dr. Rashmi.
Thank you, sir. So good evening, everyone. Today I'll be talking about pressure and fluid mechanics for anesthetists. So why does physics matter? Physics is a natural science. It explains a lot of our daily operations as anesthetists. How is the air quality optimized in modular routine? Why is it easier to inject fluid out of a 2 cc syringe than a 20 cc syringe? How do we choose the best equipment for resuscitation? How do we determine the integrity of Bain circuit or the anesthesia machine? All this is explained by physics. So for anesthetists, physics is not just an academic requirement. It is the foundation of patient safety and equipment functionality. So having said that, let us take a deep dive into fluid mechanics. What is a fluid? Any substance that continually flows or deforms under an applied shear or tangential force is a fluid. It could be a liquid or it could be a gas. Flow is defined as the quantity of a fluid, gas, liquid, or a vapor that passes through a point in a unit time. It is given by the following formula. So types of flow is broadly classified into laminar flow or turbulent flow. And the factors governing the above are the speed of the flow, the shape of the solid surface, and the fluid characteristics like viscosity, density, and compressibility. Now coming to laminar flow. This occurs in very smooth tubes at low rates of flow. Here the fluid molecules move in parallel layers, almost like sheets, like laminae, hence the name laminar flow. The fluid moves in a very predictable fashion and the layers don't mix with one another. The flow in the center is almost 2 times the mean flow, and the flow gradually decreases and approaches zero at the wall of the tube. So this gives the parabolic shape for the flow. The flow is directly proportional to the pressure gradient. and this is governed by Poiseuille's law. Turbulent flow is more disorderly, unpredictable, and chaotic. Particles move in different directions, causing swirls and eddy currents. Turbulent flow is governed by Graham's law. Now, while comparing the velocity profile of laminar flow and turbulent flow, you can see that laminar flow has a parabolic curve, as mentioned earlier. It has a very steady velocity and pressure at varying points of time. Unlike that, the turbulent flow has a logarithmic curve. So you see that it is highly unsteady with the velocity and pressure at a point that varies during various time points. So at an instantaneous point, the turbulent flow looks very chaotic. But in a time average velocity profile, you can see that the shape looks like the top of a hat. Coming to the pressure flow relationship, in laminar flow, the flow is directly proportional to the driving pressure. The resistance is denoted by the gradient of the pressure flow graph. The relationship is almost linear and the resistance is very constant. Unlike laminar flow, turbulent flow is directly proportional to the square root of driving pressure. So the relationship is very non-linear. The resistance to flow is not constant. This also means that to increase the flow, the increase in pressure should be much more in case of turbulent flow. The clinical implication of this is laminar flow requires low pressures for the same flow rate compared to turbulent flow, and therefore the energy expenditure is lower. Now we see both these fluid patterns in the human body. Let us see the flow patterns in the cardiovascular system. So laminar flow is seen in long straight vessels under steady flow conditions. This reduces the resistance and hence reduces the cardiac workload. There is an orderly flow in adjacent layers, which reduces the energy losses in flowing blood. What is also important is at a microvascular level, laminar flow is atheroprotective. How? Because in laminar flow, there is a high shear stress, which promotes the release of antithrombotic, anti-migration factors, and also promotes growth inhibiting agents. But in turbulent flow, you see a low shear stress, which is pro-thrombotic, pro-migration, and it promotes growth promoting factors, which eventually lead to vessel wall damage and plaque formation. Turbulent flow is usually observed in Kortkopf sounds and in cardiac murmurs. So what happens is, in Kortkopf sounds, you would try the BP cuff to the brachial artery and you'll increase the pressure so as to occlude the brachial artery. So when it is completely compressed, there is no flow, there is no sound. When it is partially compressed, there is a small constriction. So the flow velocity is very high. It gives rise to turbulent flow, and that gives rise to the Kortkopf sounds. The appearance of the first sound tells you the systolic blood pressure. So when the compressed vessel, the compression completely ceases, laminar flow will resume. So there is a non-constricted flow, there is no sound. So this marks the diastolic pressure. Similarly, in case of cardiac murmurs, in a normal valve, there is laminar flow, so it is more quiet. But if there is a narrowed wall, the orifice will reduce. So there is turbulent flow, which gives rise to murmur. In case of a leaky valve, there is a turbulent backflow, which gives rise to a murmur. Flow patterns in the respiratory system. So in a tracheobronchial tree, you would see both laminar flow and turbulent flow, with transitional flow also occurring. So laminar flow is seen in the smaller peripheral bronchioles and the alveolar ducts. Turbulent flow is seen in the large airways, like the trachea and the larger bronchi. Transitional flow occurs in the middle-sized airways, medium-sized bronchi. So what is the importance? For an optimal lung function, you would require both laminar flow and turbulent flow. So you see the laminar flow in small airways where the diameter is very small and the airflow velocity is relatively low. So this allows for a more orderly flow, and in an orderly flow, uniform, consistent, and efficient gas exchange takes place. Whereas you see turbulent flow in a wider airway. Here the speed of the airflow is very high. So in a turbulent flow, you would see a lot of eddies with random movement of air molecules. So this is not very efficient for gas exchange, but the speed of the airflow allows for rapid ventilation of the lungs, that is rapid in and out movement of air. So you see, in a normal respiratory system, you would want a very adequate balance of both the laminar flow and the turbulent flow for an optimal function. So coming to the onset of turbulent flow, we generally notice that as the flow rate increases, the pattern slowly changes from a fully laminar flow to a transitional flow where there are small turbulent blows to a fully turbulent flow where there are random turbulent fluctuations. So when does this onset occur? It occurs at a very critical threshold, and the Reynolds number determines this critical threshold. So what is Reynolds number? It is an index. It is a dimensionless parameter. It can be defined as the ratio of inertial forces to the viscous forces, or the ratio of fluid density to its viscosity. It is given by the above formula, where you can see that the Reynolds number is directly proportional to rho, which is the density, velocity of the flow, v, which is the flow velocity, d, which is the diameter, and it is inversely proportional to eta, which is the dynamic viscosity. So when Reynolds number is less than 2000, laminar flow is observed. When it is more than 4000, turbulent flow is observed. Between 2000 to 4000, we see something called as a transitional flow, which is a combination of both laminar flow and turbulent flow. So you can see here that Reynolds number is directly proportional to density and inversely proportional to viscosity. So density and viscosity are two things which are very important that determine the flow of a liquid. So let us go on to see what is viscosity. So viscosity is a measure of the fluid's resistance to flow. It is a measure of the ability of a fluid to resist any kind of deformation by external forces. It is caused by molecular interactions and internal friction that arises from fluid layers which move at different speeds. So here you can see water, olive oil, and honey. They all have different viscosities. Low viscosity of water is because of weak intermolecular bonds. Medium viscosity of olive oil is because of medium bonds. And the high viscosity of honey is because of very strong intermolecular bonds. Now, the clinical implication of this is viscosity affects the laminar flow. So what is density? Density is the mass per unit volume of a substance. You can see in the first diagram that in a constant volume, at lower density, the mass or the number of molecules is lesser. But as we move on to higher density, for the same volume, the number of molecules or the mass is much more. Since we've previously compared water, honey, and oil, here in this example, we can see that oil floats over water because it has less density and honey sinks because it has more density. And density affects the turbulent flow. Now let us come to Hagen-Poiseuille's law. This defines laminar flow of a Newtonian fluid through a tube. It is affected by both attributes of the tube, which is the radius and length, and it is also affected by attributes of the fluid, which is viscosity. Now let us come to clinical applications of this. So supposing you see a patient in hemorrhagic shock, there's a massive blood loss and you need to do a rapid IV fluid administration. What would we normally do? We'll either use a pressure bag, or we'll increase the height of the IV stand, or we'll use a rapid infuser. This is because flow is directly proportional to the pressure difference or the pressure gradient in accordance to the Hagen-Poiseuille's law. Now, this is a very important clinical application. Flow is directly proportional to radius to the power 4. So if you increase the radius of a particular tube, you will increase the flow also by the power of 4. So this is particularly important in airway edema, especially in infants. So you can see that in infants, the normal tracheal lumen is just about 4 millimeter. So even if there is 1 millimeter of circumferential edema, the cross-sectional area will reduce by over 75%. And because of this, the flow will decrease by 16 times, or the resistance increases by 16 times. Whereas in an adult or an adolescent, where the tracheal lumen is higher, say 8 millimeter, 1 millimeter circumferential edema will decrease it to about 6 millimeter. But the cross-sectional area decreases only by 44%, and therefore the resistance increases by only 3%. So there is a lesser consequence of this circumferential edema in adults. Now, even while choosing the cannula size in resuscitation, you can observe that in a 14 gauge cannula, the flow is about 240 ml per minute. Whereas in the pink cannula, 20 gauge cannula, it is only about 60 ml per minute. That is almost 4 times lesser than a higher gauge. So in a 14 gauge cannula, the external diameter is about 2.1 mm. And in a 20 gauge cannula, the external diameter is about 1 mm. So just a 1 mm difference in the external diameter makes a difference in flow of more than 180 ml. So now we know that we have to choose a cannula which has a higher gauge or a higher diameter. But will you choose a shorter IV cannula or a central line or a PICC line? This is also explained by the Hagen-Poiseuille's law. So you can see that a 14 gauge IV cannula, which is only which is much shorter, the flow rate is very high. It is about 236 ml per minute. But when you compare the same 14 gauge leader cap, which is about 15 centimeters in length, the rate of flow almost decreases to 170, which is almost halved. That is because flow is inversely proportional to the length. So when the length increases, the flow decreases. Flow is also inversely proportional to the viscosity. Now, what is the clinical application of this? Physiological anemia in pregnancy. Here, the hematocrit decreases, and you can see in the graph that as the hematocrit decreases, the viscosity also decreases. So the blood flow to the fetus is much higher. Also, when we use mucolytic agents in patients who have a lot of secretions, we do it to decrease the viscosity so that the secretions can flow out easily and it can be cleared. Now, coming to Graham's law, which governs the turbulent flow. Here you can see that the flow rate is directly proportional to the square root of pressure gradient across the tube, and it is inversely proportional to the square root of the density. So what is the clinical implication of this? Heliox. Heliox is essentially 21% oxygen and 79% of helium. The viscosity of heliox is almost the same as air, but the density is 6 times lower than that of air. So supposing you get a child with croup or laryngotracheal bronchitis, there is a lot of airway edema, upper airway edema. And as you can see in the picture, the lamina flow is then converted into, there's a lot of turbulence in the upper airway because the orifice is narrowed. So in these cases, when we use heliox has a lower density, so it reduces the turbulence, it reduces the resistance, so there is a better airflow. So for a certain pressure gradient, because the airflow is better, the pressure gradient can be taken as the patient effort. For the same patient effort, there is a greater flow of heliox. Now, what are the clinical applications of flow in the operation theatre? Modular OT employs laminar airflow. Now, what is laminar airflow? There is a very regulated, homogeneous, unidirectional airflow which passes through the HEPA filters at a constant velocity. And like we know, in laminar airflow, the velocity is maximum at the center. It is almost 2 times the mean flow. So it is placed in such a way that the OT table is right at the center of the laminar airflow. So because of the maximum velocity, the particles which are there are almost nil, and this keeps the operating area sterile. You can see in the graph that in the area 1, 2, 3, which is the OT table, and the area immediately surrounding the OT table, the particle size is almost like 0. It is almost like nil. So this helps in keeping the OT sterile. One more application is the Thorpe tube. What is the Thorpe tube? It is a variable orifice flow meter that we use. It has a tapered glass tube. The lower end of the glass tube is narrow and the upper end is wider, and it has a bobbin that shows the airflow. Now at lower airflows, at the lower end, the annulus, it behaves like a tube. Why? Because the length of the bobbin is going to be higher than the diameter. And we know that at low flows in a tube, you will see laminar airflow. So at this point of time, it is viscosity dependent. But as you go higher and higher, you increase the flow. The diameter of the tube is wider. The annulus behaves as an orifice. What is an orifice? An orifice, the length is less than the diameter. So here you'll observe turbulent flow. So, and you know that the turbulent flow is density dependent. So can we use the same flow meter for different gases? The answer is no. So in this diagram, you can see the flow meters of nitrous, air, and oxygen. You can see that the calibrations are not the same. There is a variation in calibration. Why? Because in flow meters, we see both laminar and turbulent flow. The calibration depends upon the viscosity and density of individual gases. So if you use a different gas for the same flow meter, the actual flows will definitely vary. If by any chance you need to use a flow meter for a different gas than what it was meant originally, then you have to send it for recalibration. Use the flow meters at high altitude. So we know that at high altitude, atmospheric pressure is lesser, therefore the density is also lesser. Our flow meters are calibrated at STP, standard temperature and pressure. So at a high altitude, at high flows, you know that there is turbulent flow. So Graham's law applies and the flow is inversely proportional to the square root of density. So the actual flow is going to be higher than the set flow. The error percentage might almost be 20% at just 4 liters per minute. So at higher flows, the error percentage is going to be even more higher. So why we have to be careful is if we use nitrous oxide and oxygen flow meters at a high altitude, these flow meters underread. That is, the flow that is set in the flow meter is going to be lower than the actual flow. And if the amount of nitrous set is slightly higher, then the amount of oxygen delivered in the mixture, the percentage FiO2 might be very low and it can lead to hypoxic mixtures. So this can be prevented by using an oxygen analyzer. Another important parameter affecting fluid mechanics is mechanical tension through surface tension and wall tension. Surface tension is seen in a liquid-gas interface or a gas-gas interface, and it affects the mechanics by altering flow patterns and resistance. Wall tension is seen in elastic tubes like bronchioles or blood vessels, and it affects the fluid mechanics by tube deformation. So when the tube gets deformed, it affects the flow resistance and leads to a pressure drop. We will see that in the coming slides. So what is wall tension? Wall tension is a tangential force that is acting along the length of the tube. The Laplace's law for a tube states that the pressure gradient across the tube is directly proportional to the tension and inversely proportional to the radius. So normally you would require a good balance between the pressure gradient across the tube and the pressure of the fluid inside the tube to prevent any overdistension or collapse. So in the human body, this tension is maintained by the smooth muscles and elastic tissue. So you can see the Laplace law over there. The wall tension is equal to the pressure gradient into the radius. So under normal conditions, there is a stability. If there is an increase in pressure, then there should be an increase in tension to balance this. And if there's an increase in radius for any reason, then the tension also has to increase to create a balance between the pressures. So what happens if there is a fall in pressure in arterioles? So there is less distension. So that could reduce the radius a little, but the tension is maintained by the smooth muscle. So the ratio of the tension and radius is increased and the pressure gradient is also maintained. So because of this, the vessel contracts and it does not collapse. Clinical implication, this may not happen in an aneurysm where the tension is not going to be seen the same across the vessel because of the weakening of the vessel valve. So anytime the pressure gradient increases, it can cause rupture. So there is also something called as a critical closing pressure of vessels and bronchioles. This is a theoretical thing which can be seen in the cardiovascular system or in the respiratory system, that if the pressure decreases beyond a certain value, then the blood vessels or the bronchioles can collapse. What is surface tension? Surface tension is a measure of force at the interface between two immiscible fluids. Immiscible fluids are fluids which do not mix. This force arises due to the intermolecular attraction between the molecules at the surface of the liquid. So the Laplace's law for a spherical structure says that the pressure gradient is directly proportional to 2 times the tension, that is the surface tension, and it is inversely proportional to the radius. So according to law of Laplace, if you have 2 bubbles with the same surface tension, the smaller bubble will have a higher pressure. So why is this important? The surface tension of moisture, which is present in the alveoli and alveolar ducts, can lead to potential instability in the lungs. How? So when the radius of the ducts and the alveoli, they diminish during expiration, the pressure across the wall tends to rise because of Laplace's law. And this can lead to collapse of the alveoli if the surface tension is constant. Now, what does the surfactant do? It is a lining fluid. It acts by two mechanisms. One, it reduces the surface tension of the fluid lining the alveoli, and it also makes the surface tension variable so that when the alveoli distend, the surface tension increases to prevent it from bursting, and when the alveoli contract, the surface tension decreases, preventing collapse. In premature infants, this surfactant may not yet be present, and because of this, problems can arise because of alveolar collapse. Now let's move on to Pascal's principle. So Pascal's principle states that a pressure change in a confined incompressible fluid is transmitted equally and undiminished to every portion of the fluid and the container walls. It is given by the formula P1 is equal to P2. So the ratio of the force divided by the area, the cross-sectional area, should be equal on both sides. So this is the basis for hydraulic systems which multiply force. So how do they multiply force? They use different piston areas. So from a smaller input force, you can generate a larger output force. So what are the clinical implications? Tracheal tube cuff inflation. So once the cuff is inflated, the pressure you feel in the pilot balloon is almost the same as the pressure that is being exerted by the cuff inside the patient's trachea. This is because of Pascal's principle. In invasive blood pressure monitoring, the pressure from the arteries or the veins is transmitted to the fluid-filled system through a transducer, which converts this physical pressure to an electrical signal, which is displayed on monitor. Again, this is because of Pascal's principle. Coming to syringes and injections, applying force to a smaller area of the plunger, it generates more pressure that is transmitted through the liquid, resulting in a force, which is seen at the needle tip. So normally, if you have to dislodge a clot in the central line, how would it be easier in a 2 cc syringe or would it be easier in a 10 cc syringe? Now, the normal tendency of people is to try to dislodge it with a 10 cc syringe or a 5 cc syringe. But if you use a 2 cc syringe, because the area of the plunger is smaller, with the force that is generated, the pressure that is generated is much higher. So it is easy to dislodge the clot with a 2 cc syringe. For the same reason, filling a 2 cc syringe is easier than filling a 10 cc syringe. Now, before we go to Bernoulli's principle, let us see a few fundamental fluid laws. One is law of conservation of mass. It is also called as the continuity equation. It says that for a fluid in a steady flow, the mass flow rate is constant, meaning what flows in must flow out. So a mass of fluid that enters through a point A1 should be the same or equal to the mass of the fluid that exits at a point A2. Now, what happens if there is a constriction at a point A2? The A2 area is narrower. According to the law of conservation of mass, the mass flow rate should be constant. So what happens is the velocity increases to maintain the equilibrium. Law of conservation of energy says that energy cannot be created or destroyed. It can only be transformed from one form to the other. Both these form the basis of the Bernoulli's principle. This was described by Daniel Bernoulli in 1738, but published much later in the 19th century. So for a non-compressible fluid, a non-viscous fluid in lamina...
Dr. Rashmi, another 5-10 minutes, I think we need to wind up, if possible, please. Thank you.
Yes, sir. So for a non-compressible fluid, non-viscous fluid in lamina flow, the sum of the kinetic energy and potential energy per unit volume, it remains constant at all points along the line of flow. So as you saw earlier, an increase in velocity of a fluid will occur simultaneously with a decrease in pressure. So velocity of the fluid corresponds to the kinetic energy and the pressure corresponds to potential energy. So the sum of the kinetic energy and potential energy should be equal at both points A1 and A2. So the consequence of Bernoulli's principle is the Venturi effect. So you know that when there is a constriction, the velocity of the fluid increases, so the pressure decreases. Now imagine if you keep a small entrainment window at this constriction, at this venturi constriction. When there is a subatmospheric pressure, this window can entrain air or liquid. This is called as jet entrainment, and this is the venturi effect. Now, adjusting the diameter of this constriction can allow the control of pressure drop. Now, what is the clinical application of the venturi effect? One is the venturi mask. So, venturi mask is a fixed performance oxygen therapy device. That means irrespective of the patient's rhythm and rate of breathing, the FiO2 delivered is going to be fixed. Now, how does this happen? The venturi valves are color-coded according to various degrees of venturi constriction that allows varying degrees of pressure drop, and the size of the entrainment inlet is also different. So when you see the example over here of a yellow valve with an oxygen flow at around 8 liters per minute, it entrains almost 36 liters of air to provide a total flow of around 45 liters per minute. So the FiO2 can be calculated to 35%. The FiO2 can be calculated in a similar way for other valves also. Another application is a nebulizer where a compressed gas is used as a driving fluid. It enters the center through a venturi constriction, and it entrains the liquid or the medicine from the side tube, and breaks it up into droplets suitable for inhalation. Another application is the Pethick's test, where you can check the integrity of the inner tube in a vein circuit. So what happens here is once the oxygen flush is activated, air through the inner tube, which acts as a venturi constriction, the velocity increases and the pressure drops at the exit. So the air in the outer tube is entrained and the reservoir back collapses. But if the inner tube is damaged, no entrainment occurs and there is no collapse. This is also used in jet ventilation and in injectors. Now coming to a Coanda effect. The Bernoulli's principle and the venturi effect lend themselves into this very interesting phenomena called as Coanda effect, which was described by Henry Coanda, who was actually a Romanian aircraft designer. He said that any fluid jet that comes into contact with a curved surface will cling to the surface without altering the direction of its flow. So the flow of the fluid will conform with the flow of the contour of the curved surface. Now, how does this occur? The mechanism is as such. So for the first, initially you can see the venturi effect. The air is entrained at a low pressure area. Now imagine if you keep a solid white surface at one side, the atmospheric pressure acts at the other side only. But the low pressure is also there on the side of the white surface. So what happens is the atmospheric pressure pushes the fluid to cling onto the white surface. And this clinging is even more if the surface is curved because of the presence of low pressure vortexes. What is the clinical application of this? So Coanda effect can be seen in any branching tube system. So if there is a constriction before any bifurcation, there is an increase in velocity and there is a decrease in pressure. And the liquid preferentially flows to the branch with a lower pressure. So if there is a mucus plug at a tracheobronchial tree, there could be an uneven ventilation, and atherosclerotic plaques in the bifurcation of vessel walls can lead to uneven perfusion. It can also be used in ventilators that use fluid logic devices. These are essentially a valve mechanism with no movable parts. A tube or a control nozzle is just inserted at the exit of the narrow tube. So when the gas flows out of the venturi construction, the flow through either side of this control nozzle can switch the flow from one tube to the other tube. So what happens is when you use such devices, the number of valves and moving parts
Dr.
are
Rashmi,
lesser.
I've been asked that you're getting towards
another
the end.
2 minutes.
Yeah,
2 minutes.
Sure.
Sorry, sir.
Yeah.
So the resistance is lesser and easier for transport. So coming to the last part of my talk. So we've all seen all of these physical principles. What is fascinating in these principles is they were in use in India long before Venturi principle was even published. So Hawa Mahal was built in 1795. This structure has 5 stories with 953 jarcolas, which are small windows with jalis or perforations in the facade. So what essentially happens is the air passes through the narrow windows, the velocity rises, pressure reduces, and more air is entrained in the jalis. So this leads to a cooling effect along with the fountains that are present inside the Hawa Mahal to give an air conditioning to the whole area during hot desert summers. So we also have the Kumili Tumbu, which is the Tamil ancient lake irrigation system developed during the Chola period in the 9th century. So these structures are essentially very present in the lakes. They are used to divert the water to the canals in the irrigating fields. So what you can see is a stone which usually covers the inlet. When the stone is lifted, water enters the stone box, and a venturi effect is seen. So in the stone box, on one side, there is a lot of perforations and the silt is entrained. So the silt with rich water is sent into the canals and it makes the fields more fertile. And another application is this also causes natural desilting of the lake. So this was there in the 9th century, almost 1,000 years before the venturi principle was even described. So what we can see is ancient Indian achievements. They show that the mastery of physics just simplifies our existence. So we should continue their legacy of learning. So with that, I conclude my talk. I'm sorry if I took a lot of time. Thank you.
Thanks, Dr. Rashmi, for a wonderful talk on fluid mechanics, which is a very simple topic, but you explained it very nicely. So to quickly summarize, Dr. Rashmi spoke about concept of fluid and fluid mechanics, laminar flow, turbulent flow, Hagen-Poiseuille's equation and its applications, especially about the size of the cannula, how it makes a difference to resuscitation, size of the endotracheal tube, the concept of heliox and Bernoulli's principle, and of course the venturi effect, which we all use in our anesthesia day-to-day applications. Just to quickly add one thing, as far as postgraduate students are concerned, of course there are two types of flows, laminar flow and turbulent flow. Just for extra knowledge, there is one more type of flow called as a transitional flow, where the flow is between laminar and turbulent. That depends on the Reynolds number. Okay, so it has characters of both laminar and turbulent flow. If Reynolds number is less than 2000, they say it's laminar flow. If it's between 2000 to 4000, it's a transitional flow. More than 4000, it becomes a turbulent flow. So that's all that we have. So thank you, Dr. Rashmi, for a wonderful explanation of fluid mechanics.
Thank you, sir.
Sir, there is a question in the chat box, sir.
Yes, sir. So shall I ask that question, sir? I think I just noted down. So I think this question is regarding fluid dynamics. I think so it'll probably be to Dr. Rashmi. The question is, what precautions regarding fluid dynamics should we take when we are giving infusions in stiff tubing? So you have a stiff tubing joining the compliant tubing. So first tubing is a stiff tubing, the other is a compliant tubing in the ICU. Probably I think they're looking into like we are giving fluids through fluid infusion pump or a syringe pump. The initial tubing is a stiff one because it's very thin, and that is connected to a wider tubing when it is going into the patient's IV, this one cannula. So regarding fluid dynamics, what changes can happen, because first it's passing through stiff tubing, then a compliant tubing, and what precautions we need to take? Over to you, Dr. Rashmi.
So when it moves from us, if the tubing is more stiff, then the tension would be different. The tension would be higher. So the flow is going to be lower. So we have to keep in mind that probably the flow is going to be lower initially, and when it transitions into a more compliant tubing, the flow is going to be higher.
You expect the fluctuations in the pressure and the flow, isn't it? Initially, yes, there is a lot of resistance.
Yes.
Suddenly, it goes into a compliant tube, resistance is lot. So you can expect a
yes,
pressure spike in
yes,
terms of flow, and the flow also will be irregular. And
yes,
I think there is also a risk of some air bubbles getting trapped or some regurgitant flow. These things can happen. I think especially if you're giving through a syringe pump, I think you will see this difference. You
yes,
can see. So
yes.
the question,
sir, even in
yes, sir,
pressure monitoring lines,
yes, sir,
for arterial we are using that stiff line. But
yes, sir,
same thing is used for venous. It may be a problem, but again, I think personally we cannot predict that flow, because we are predicting the flow, the proximal tubing. That is,
yes, sir,
proximal tubing. If it is stiff, it is going to be stiff only.
correct.
Because that is going to be the deciding factor. And distally, what may happen, I don't think that it will have some influence on that.
Correct.
But he would have asked that specific question, thinking that we are mixing so many lines, extension tubings.
Yes, yes,
That is
yes.
also from, but we are thinking that 10 ml per hour means that 10 ml is going to go into the distal tubing also.
Correct.
Because it is going to go for 10 ml per hour only. It cannot increase as it is a fixed flow.
Correct.
But when we open that IV fluid bottle, then it may make some difference. But
Yes.
again, the decision making is the first static tube.
Yes.
That is high low compliance.
Correct, sir.
That's
That's it.
so. If there are no other questions, sir can pass the concluding remarks.
So I would just like to, first of all, thank Dr. Meenakshi Sundaram sir for giving us the excellent opportunity here in the Anesthesia Department of Bangalore Medical College. For myself to moderate the session, Dr. Rashmi, Dr. Smitha, and our resident, Dr. Varshini, which is a wonderful exposure for her, I thought. So the three topics that were covered today were, of course, the humidifiers by Dr. Varshini. We are using humidifiers day in and day out of the anesthesia practice, especially the HME filter. Then the gas loss by Dr. Smitha. It's a very important question asked in theory as well as in the practical exams for all the postgraduates. So she explained it very nicely, I thought, with the good illustrations, Boyle's law, Charles' law, all the gas laws and how the universal gas constant is derived. Everything she explained very nicely, I thought. And lastly, Dr. Rashmi, I spoke very well about fluid mechanics, explaining the principle of different patterns of flow, the laminar flow, turbulent flow, how to derive the Hagen-Poiseuille equation, and most importantly, the clinical day-to-day application of the Hagen-Poiseuille equation, why using a broader gauge cannula, why we always use, you put two large bore cannula, that is explained by this, the increase in diameter which increases the flow so much. Then how we apply to the size of the endotracheal tubes, how it makes a difference. Then application of heliox, then surface tension, the various application of Venturi effect, right from the jet injector to ventilators to the Venturi mask, different colored, how they give different FiO2s. So all this is very important. So I think all the speakers spoke very nicely and have explained in details. So thank you for the opportunity, sir.
Thank you, sir. So on behalf of Puthukkottai ISA City branch, I should thank the youngest speaker, Varshini, who has dealt with humidifiers extensively up to ultrasonic nebulizers. She has gone. That is the reason why she was overshooting the time. And it was followed by Dr. Smitha. That is gas loss. Really, Dr. Smitha and Dr. Rashmi, their illustrations are very good. So I think both of them are having an illustrious career ahead. So they will be matching Dr. Vinay's standard because of these illustrations. It is excellent actually. So when the postgraduate is talking about ultrasonic nebulizers, highly advanced mode, Dr. Rashmi was talking about Rajaraja Chola. Because I will be participating in the poetry competition in our temple because Rajaraja Chola belongs to us. Tanjavur big temple. So I thank, and necessarily the moderation was really royal because of the Royal College degree or back to Medical College, I don't know. It was royal, and really we are very happy, and we are ending it in a smiling note. So I thank all the four speakers, and I request Rimpa Clearnet to pass the concluding remarks and close the session.
So thank you so much everyone for joining this session. Clarnet is really glad to have all these brilliant people together. So with all your permission, I'm closing the session for today and looking forward to hosting you again. Thank you so much, everyone.
Thank you. Thank you.
Thank you, sir. Wish you all a very Merry Christmas and Happy New Year in advance. Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.